And what I'll do is open up the presentation. Okay. Okay, so can you all see the screen? If you could maybe just mention in chat whether you can see the screen. Thank you, Stephen. Yeah, that's excellent. I'm not sure what difficulties they've had at Meetup here, but a few things haven't quite worked out, but that doesn't matter because we'll get into this. Oh, there's more people coming. Thank you for that. Oh, right. I have to confess, I've not done this prep before. That's fine. Yes, I've run. I used to use Eventbrite all the time, and I have just moved over in conjunction. I was asked to co-host with Terrell France, who's the senior lecturer at the University of Harrisburg Science and Technology in Pennsylvania, who I've been doing a lot of work with. And he's wonderful to work with. And he asked me to host this meetup group, Quantum Computing Australia. Okay, look, I'm going to start because I don't like to keep you long. So it's 6 minutes past 5, so I apologize for that inconvenience. And I'll just let people in as they come along. There was supposed to be a couple of dozen, but really something has gone wrong with Meetup. But with no further pause, let's go into this amazing experiment that's only 20 years old. And it's changed the way physicists look at not just quantum computing, but the nature of the universe. What you're about to learn is absolutely incredible. And I hope you understand the double slit experiment and the observer effect and the wave particle duality. I will go over it at lightning speed, but it's so much better if you understand that, because the delayed choice quantum eraser experiment is merely the double slit with entangled photons. So in the double slit, traditionally we just put through normal photons. And in this one, we actually put through entangled photons through the double slit. And what it showed was some amazing differences, which absolutely, like everything to do with quantum physics, it was just absolutely unbelievable what happened. Just by putting entangled photons, so that means photons that will always be the same, that have the same spin, etc., through the double slit. So let's see how that worked. Okay, now here is the delayed choice quantum eraser experiment. If you've never seen it before, it looks very complicated at first, but it truly isn't. And I'll take you through this step by step. So there's absolutely no need to worry about it being difficult or anything, because I'll just annotate. I'll get my mouse up and annotate it. So this is merely the double slit here. So this is just like the opening slide from the double slit, and here are the two slits. But what happens is it hits a BBO crystal. And don't worry, I'm only giving you an overview now. I will go into detail on all of this equipment, so don't worry. But this BBO crystal, I forget what it stands for now, barium borate oxidized crystal, what that does is entangle the photons. So the photons immediately go through the slits and then they're entangled. And then they go through a prism which sends them in different ways. And you can see here the red is a pair of entangled photons and the turquoise is a pair of entangled photons. And because of the prism, one goes that way, on the red one goes this way, and one goes the other way. And then the beauty of this is that it goes through all of these smoke and mirrors, which are going through these slits here is what's called the witch way. And if you remember from the double slit, we're not allowed to know the path of the electron, Heisenberg's uncertainty principle. So we're not allowed to know the which way. And if we do, it collapses the wave function. And I'll explain these in a second, and don't be afraid to ask questions in the chat. Well, I'll check every so often. But it's amazing that the photons are entangled photons, which must always be the same, are sent through by the prism. I'll just see who someone's got a question here. Oh, that's all right. No, that's okay. The entangled photons are sent in different ways to these detectors. There are 5 detectors, detector 0, and you must look at them. At these detectors, they actually show either an interference pattern, which means it is a wave, or a clump pattern, which is 2 vertical lines, which means the photon arrived there as a particle. And I'm going to quickly go over, please don't be confused with anything as yet, if you're not familiar with them, because it's relatively easy to follow. Someone else trying to be admitted here. Let me just admit a couple of people. Hello, Ganesh, and hello, Sharan. We haven't really started, so that's fine. I hope you, oh. Okay, so, yeah, you should be muted. Okay, so we have the entangled particles, the entangled photons going through a different way through this system. And the quantum eraser part of the experiment, and can you, someone's on, has unmuted themselves. Please, I've given you that facility, but please mute yourself, otherwise you come across in the presentation. So by sending the photon in an entangled pair, and sending one way and one another way, we can do amazing experiments, which this is. And I'll go through the differences one by one. Okay, there's more people trying to get in. That's fine. Okay, so that's this is how it looks, but I'm going to go through it step by step. I keep stressing that simply because I don't want you to feel lost. And if you are lost, just ask a question in the chat. But I don't expect you to understand all of this yet. I'm going to explain every piece of equipment here and what it's doing. Okay, so what was the point of the delayed choice quantum eraser experiment? There were 2 issues. with the double slit, I might have to mute everybody here because someone's. Okay, if you can, yeah, just please, I'll mute you all. So you're going to have to use the chat because someone was coming through, but not to worry, it shouldn't happen anymore. Okay, so what was the point of the whole delayed choice quantum eraser experiment? One of the most amazing experiments that has ever been conducted. It was 2 points. First of all, with the double slit, which I'm going to go over, but hopefully you're a little bit familiar with. With the double slit, people were saying, well, hold on. When you measure the photon, you are actually disturbing it because measurement is by sending a photon to collide with another photon and come back and say there was a photon there. So, and scientists said, hold on a minute, the act of measurement is affecting the pattern, whether it was interference or clump. So this experiment doesn't have any measurement. It just has a way of manipulating with smoke and mirrors. It can mean that we can know which way the photon traveled. And then it's interesting to see what effect that has. So no measurement. Secondly, it shows us that events, the future can affect events that have already happened, at least in the quantum realm. But remember, we're all made up of quantum particles. So the experiment was only done in 1999, not that long ago, by Kim, Yu, Kulik, Shi, and Scully. You can think of it as the double slit with entanglement, and the two concepts that you have to understand are the which way and the delayed choice. The which way is which slit, it happens at the first detector, which slit does the photon travel through? And the delayed choice is that because of the apparatus in the experiment, and the actual hitting of the back screen is delayed because it's going through mirrors and beam splitters. And again, I'm going to explain all this, so don't worry. Now, look, this is very quick because I did say in the presentation opening that it's very important you understand the double slit, because if I start explaining that, then we don't have time to do a deep dive on entanglement. So the double slit is just a well-known experiment that shows the wave-particle duality of light. That light can be a wave and a particle and at the same time. It is in superposition until it's observed. So if we look away, when you shine a photon through the slits, it shows what you can see at the back here. Let me annotate this so that you can see, otherwise you'll lose the... so here I am. So here's the back screen, the front screen with two slits, the back screen. And this is very important because this comes into the quantum eraser later. At the detector, you see either a what's called an interference pattern or a clump pattern. You will see one or the other. Now, if it's an interference pattern, it means that the photon was a wave. If it's a clump pattern, two vertical lines, it means it was a particle. So at these detectors, what we're looking for is whether there's an interference pattern or a clump pattern. And the observer effect just means that if you measure or observe the photon, it changes from an interference pattern into a clump. Are we all okay with that? Because that is important. So the observer effect and the Heisenberg uncertainty principle, which basically says we're not allowed to know the path the photon took or will take. Whereas in the classical world, the Newtonian world we live and operate in, if I throw a ball, if we know the weight of the ball, the mass of the ball, the air resistance, the acceleration I impart on the ball, we can know exactly where it's going. In the quantum world, you can't know any of those things. You cannot know the location and the momentum of a subatomic particle. And that's what causes all this amazing mystery of quantum physics. Because this doesn't happen in the Newtonian world, the classical world, that you cannot know these two things. And I stress that it's not that we haven't got sophisticated equipment, it's the fact nature, it appears, and interpretation is that nature is actually not allowing us to know. Because as soon as we put a camera there, we want to find out the wave, the interference pattern changes to a clump. Okay, so let's get into this. I'm going to now go between here and the equipment, because I need you to understand, all of the equipment. So let me get my trusty spotlight again. And just letting another person in. So here, I'll go through the equipment one by one. So this is just a photon coming in. It's going through the double slit, just like the normal double slit. But as soon as it goes through, it hits what's called a BBO crystal, barium borate oxide crystal, which creates two entangled photons. And those entangled photons will always be the same. They will always give the same result. So it immediately goes through there, and then it immediately goes through a prism, which deflects the entangled pair. So it forces one entangled photon to go one way, and its twin to go the other way. So there's an entangled pair here. One is made to go this way to detect a zero, and the other one is made to go this way, which is far more complicated. It goes through a prism, which then directs it onto a beam splitter. So this here is a beam splitter, and we have three. A beam splitter is an amazing piece of equipment, and it's a combination of polarization, vertical and horizontal, which I won't go into now. But the point is that when a photon hits a beam splitter, 50% of the time, it will go straight through. So this photon here is coming to beam splitter B, and it just goes through 50% of the time. And then 50% of the time, it will bounce off. And that's the same with any beam splitter. Now, these ends here are just mirrors, so they will reflect every time. So here, my 50% of the time it will go through the beam splitter, it will hit the mirror, 100% of the time it will reflect. It hits another beam splitter, 50% of the time it will go through, 50% of the time will be deflected. So you can see that the entangled pair, each of the entangled photons goes through the experiment, through the apparatus in a different journey. And the magical thing here is by examining the detectors, we can see whether it hit that detector as a wave, in which case you'll get an interference pattern, or as a particle, in which case you'll get a clump. And yes, and that's quite a lot to take in. Now, are there any questions? Please pop them in chat now, and I'll give you a couple of seconds, and I'll answer. If I don't see any questions, I'll assume that you're all sort of with it. Okay, I can't see any messages coming, so I'll assume you're all okay at the moment, which is great, fantastic. Okay, so we have the BBO crystal, which entangles the particles. We have the lens, which focuses on a detector, the beam splitter, 50% chance of going through or being reflected, the prism, which redirects the photon, and then importantly, at each detector, we have a different pattern, an interference or a clump. Now, what this experiment was going to prove was that if we know which way the photons traveled, it will be a clump. But if we don't know the way it's traveled, which slit it went through, if we don't know that, it will have an interference pattern. So, now, this is the crux of it all, basically. So let me get my annotation up again, and I'll use the stamp this time. And I'll drag that out the way. So, yeah, what I'm going to do now is, let me first of all highlight the detectors. So here's detector 0, here's detector 1, here's detector 2, detector 3, and detector 4. So you can clearly see where they all are. Now, this is the crux of it all, and there's no measurement happening, remember. I'm going to now follow the path of it. There's two pairs, there's a top slit pair of entangled photons and a bottom slit pair of entangled photons. Now, at detector 1, let's look. So here I'm going to take the top entangled photon, which is in red. So it's coming through here as an entangled photon. It's entangled. One entangled photon has gone through here and it's reached detector 0. Its twin particle has gone all the way down here and all the way through here, and we don't have to worry about where it's all gone. We just need to know at this stage it's gone a different way. That's the top entangled pair. Now, the bottom slit entangled pair has come in here, it's been entangled, it's gone through the prism, and then the top one has gone here. So, detector 0, let's forget all the other detectors, just detector 0. So I'm now asking you, so if you could try and answer in chat. I'd be very grateful if somebody can answer this. But you can see that at detector 0, we don't know which slit it came through. It could have been the top one from the top slit, or the top one from the bottom slit. We don't know. So if we don't know which way it's gone, can anybody tell me what the pattern we would expect to see at D0? Now, I know when I'm at presentations, I absolutely hate it when the organizer asks a question, but I'll just give you a few seconds. Can anybody, oh, thank you, Sheetal. Yes, and you're exactly right. It's an interference pattern. Why? Because we don't know its path. So because we don't know, nature says, I'll say nature, there's a lot of different interpretations, but nature doesn't know whether it's the top one or the bottom one, or the top photon of the bottom slit. We don't know which slit it went through. So there's an interference pattern. Now, let's compare that. Now, I could go through each detector, but let's just compare that with detector 3. And let's look at detector 3. Now, detector 3 can only come from the bottom slit. So we know, we're not measuring it, but we have the potential to know that at detector 3, we know which slit it went through. Because if it's going through the red, you see the red, no matter where it's deflected, no matter where it goes through, no matter what happens, it cannot get to detector 3. Detector 3 can only be the bottom entangled photon going through the bottom slit. So the photon comes through here, it's entangled, it goes through here, and it goes through a prism. And then it gets to beam splitter A. Now, it may well go through, because remember, a beam splitter gives you a 50% chance of going through. So it may well go through and carry on through the system. But 50% of the time, it will be deflected and it will come here. And it will hit D3 on, every so often. 50% of the time, it will end up here. But no matter what happens, it cannot come from either entangled photon going through the top slit. Therefore, we know, even if we're not, I have to stress this, please don't worry about me saying the same thing time and time again, because I think it's important, because it is confusing. And I think by just going over, I'm not ashamed to say the same thing again and again, because at some stage the penny will drop. But here, it can only come from the bottom slit. So we're not measuring it, but we know it's come through the bottom slit. We know the which way. So I'm going to give you another question. So I'll just check my chat. Oops, come on. Now, at D3, where we know which way it comes, can someone tell me what pattern would we expect to see at D3? Stephen, thank you. Excellent, Stephen. It is the clump. Now, That is amazing. Think about this for a second. This is a subatomic particle. This is a million times smaller than a speck of dust. Yet, when it goes through complicated apparatus, I mean, it's not that complicated, but complicated apparatus that you see here, how can it change its fundamental form simply by, how does it know whether an observer can find out which way it's traveled? It's amazing. And by the way, if you think it can't get weirder than this, it can, and I'll explain that in a few minutes. But think about what's happening. How can that be? It's just amazing. There's no measurement, there's no interference. It's not one photon hitting another and then knocking it to one side. This is incredible. How on earth can that photon know if there could possibly be an observer who's not even observing, but could possibly know which way it's gone, and thereby completely change its format, its empirical formation from a wave to a particle? Now, we could go, and we'll make an exercise of just going through. So at D0, we can see it comes from the red or the blue. And then let me look at D4. D4 can only come from the top slit. I think you guys know now, but what does that mean the pattern will be? It will be a clump pattern because we know it's from the top slit. And believe it or not, that's what you always get. But let's say it went through the beam splitter, hits the mirror, and then goes through beam splitter C and hits D1. It could easily have done that, but that way it could also have come through here, gone through, reflected, and come back. So at D1, it could have come from either. So we have an interference pattern. Now, this experiment has been conducted millions of times. And the result is always the same. It is what we would expect. If there are two lines coming in here, a red and a turquoise, I'll call it. If I've said blue, it's obviously blue or turquoise. If it can come from either, then we find interference patterns. So always D1, I'll just take the spotlight. D1 is always interference. D2 is always interference. D3 is always clump. D4 is always clump. Now that is amazing. I mean, you know, I'm going through this at 100 miles an hour, but again, think about the ramifications of that. How can that be the case? How can this subatomic particle change its empirical format on a whim almost? Oh wow, it's just fantastic. Now guys, can it get any weirder? Well, this is quantum mechanics, so you know the answer to this, don't you? It can get a lot weirder. Because there's something I haven't told you. We're now going to introduce time into this experiment. Now, you can see, let's just take the red, and where's my stamp? So we're only going to take the red. The top entangled photon goes on this short distance to D0. Short, not uncomplicated, direct, and it hits D0. Its entangled partner, who must always show the same spin, i.e., it must always, if the top entangled photon, excuse me, if the top entangled photon is a wave, then its twin has to be a wave. If the top entangled photon is a particle, then its twin entangled photon has to be a particle. So that one's gone that way, but this one, it takes longer because it's going, in the case of D1, it's traveling a lot further. It's going through beam splitters, it's bouncing off mirrors, it's going through another beam splitter, and it ends up at D1. So there's a time difference, albeit measured in nanoseconds. But there's a difference. Now, here's what the amazing thing is. Well, it's all amazing, but this is unbelievable. When we send a photon through, this one registers either a clump or a interference. Let me just carry on. And there may be a question from that, which I'm happy to answer, but I want to make it very clear and simple to you. So this goes through and it makes a measurement at detector 0. Now, let's just say let's in fact say that its partner goes through here, la-di-da-di-da, and gets to D1, which is an interference pattern, then D0 will show an interference pattern as well. Perhaps what you would expect. However, when the first one goes through and hits D0, let's just say the second one goes through here, is deflected from beam splitter B, and has a clump pattern at D4. Well, if we look at D0, it will be a clump pattern. And this experiment has been done thousands and thousands of times, yet it will, the entangled photons will always give the same result. I've got it. Thank you, Sheetal. I'll answer this question as I go. So you're saying that the wave function has collapsed at D3 and D4? Yes, that's exactly what I'm saying. We showed, thank you for that question, Sheetal. So we send photons in. We have the ability now to send one at a time. So the first one might be deflected and hits D4, in which case, and this is not an entangled photon, just an ordinary photon. It would go through and it would be detected at D4. And the wave function would be collapsed and the same as D3. So Sheetal's completely correct. And again, there's been no measurement here. I don't mind saying that all day. However, remember the second entangled photon, anything that goes through here, and this is what we call the quantum eraser, where even though we, like here at D3, we know which slit it's gone through, D3 and D4. We know D4, top slit, D3, bottom slit. But if you send another photon through and it goes through, so that it's just chance, it's going through the beam splitter, and then it will be an interference pattern. But what I'm saying to you, and this is the important thing, whatever happens, D0 will always, and I mean after millions of experiments, it will always equal the same as what its entangled photon ends up as. So its entangled photon, by chance, will end up at D1, D2, D3, or D4. This is the delayed, because it takes longer to go through this apparatus than the other one. So we're delaying whether it's, and it's by chance, whether it's going to be an interference pattern or a club. It just depends on whether it's deflected off the beam splitters, or it goes through both, or it goes through one, is deflected off the other. We don't know. But somehow its entangled twin already knew what was going to happen in the future. It knew, and I have to stress this has been done thousands and thousands of times, but it knew what its twin entangled photon, how it was going to go through the system. So no matter what, something very, very strange is happening. Either the entangled photon that goes through the apparatus is somehow changing the event of D0. So it's saying, hey, look, I went through the first beam splitter, but then I deflected off the second. Therefore, you have to be a wave or a particle, because that's what I am now. And that's it. Do we all think that's just absolutely amazing? Do we have any, let me get out of that. Yes, there's a question here, thank you. I love it. It's not a question, it's Sheetal going, wow. And same with Stephen, so thank you both. Yes, what can I say? What I can say is that we don't know what's happening. We don't know. Yes, Stephen, it could well be going backwards in time, or somehow, it's one or the other, isn't it? It's either the first particle, entangled photon, it's, excuse me 1 second. Well, let me answer Sheetal's question. So who's to say that D4 doesn't or shouldn't mirror D0? Yes, but Sheetal, we don't know. By the time when the first entangled photon hits detector 0, we don't know which way its entangled photon is going to go through the beam splitters. But what happens is when it goes through and hits D4, then D0 will equal D4. When it goes through and equals D1, the first D0 will equal D1. Somehow, D0 knows how its entangled photon is going to travel through the apparatus. Now, it's either the second one tells the first one and changes events that have already happened, because the entangled photon, the top one, has already hit detector 0. So when the second one eventually gets to where it's going, it then does, how does it tell it to, hold on, you went as a wave, you really should be a particle, because that's what's happened to me. So it's really amazing. Wow. Can it get any freakier? Yes, it can. I'm loving this, as you know. There's one more thing I want to tell you. Now, this is just, I zoom in on detectors. Oh, I might tell you, just so you know, I dislocated my shoulder a month ago. And after typing, it's a month ago, so I don't need surgery, and it's going to get better, but sometimes it's sore. So if you hear me acting like a big sook, that's me. John Wheeler, a Gedanken is a thought experiment. John Wheeler is one of the greatest physicists that's ever lived. There have been some wonderful ones, like Einstein. Einstein's achievements are almost unbelievable, what he achieved. 4 papers in 1 year. His Annus Mirabilis in, I think it was 1912, could be 1905. No matter what, unbelievable. So Einstein's fantastic. But John Wheeler, who only died about a decade ago, is unbelievable. And he came up with a thought experiment based on the predictions of the delay. Actually, it's the other way around. The delayed Choyd quantum eraser half proved his Gedanken. I'll tell you his Gedanken in a second. Einstein used Gedankens all the time, I might add. So it's a German word, which I think means thought. If any of you are German, please correct me. But what are the ramifications for quantum computing this time? So quantum entanglement, it's called temporal quantum entanglement. So quantum entanglement, you've got a subatomic particle here, one on the moon. You change the one here. You collapse the wave function of the one here. That's what happens. You observe the one here, and that turns into either a wave or a particle with a 50-50% chance. The qubit, don't get locked up in this. And the one on the moon collapses in the same way. And that happens, that's been done millions and millions of times, and it always works. So what it means for quantum computing is that in quantum computers, the beauty of the exponential processing of the qubits is down to the fact that you've got superposition. So of a qubit, it can be in superposition, so not just 1 and 0. It can be 1 and 0 and all these complex and imaginary numbers in between, representing interference superposition. And once you put on 2 qubits, you get entangled then. So not only that's what gives you the exponential, so now you've got one great big system. Whereas in binary, you don't have that. You have, number one, you only have a choice between 1 and 0, but the second bit can't be fundamentally, empirically entangled with the first one. Sure, it can take the result of the first one and alter it, but it's not entangled. So you can imagine the power of the more qubits you have, it's 2 to the n. So with n number of qubits, you have 2 to the n possibilities. But what it means for quantum computing is that because of this temporal quantum entanglement, because quantum entanglement works over time, it means you could have a decryption cipher which doesn't exist yet. So you could set a code whereby the breaking of the code is written on atoms that don't exist yet. Bear in mind, we're talking nanoseconds different. but that doesn't matter. It means that theoretically, Gedanken, that's possible. What's the ramifications for our universe? Wow, well, I'll leave you to think that. You Mr. Sid, oh, I've got something in chat. Of course you can change the future, but you want to change the past. Yeah, okay, thanks, Stephen. Yeah, that's a philosophical. The good thing about what I love everything about quantum physics and quantum computing. But one of the great things is quantum physics, and why this new upcoming paradigm shift of quantum computers is going to be so different, is that quantum physics affects the universe. It's not just science, it's philosophy, epistemology, theology, religion comes into it. It brings, because we don't understand it, we don't know what's happening. Yes, it's feasible that in 10 years, 20 years, 50 years, our whole planet will be run, and believe me, it will, by quantum computers that we don't understand fundamentally how they work. I mean, with a supercomputer, digital computer of today, we know how it works. We send through a voltage, it's either 1 or 0, boom. Depending on how much voltage we send through, it goes through a transistor on a silicon chip, and we can work that out. But with a quantum computer, we don't know how these calculations are being done. So time, which I don't know whether you guys understand the law of entropy, which is the second law of thermodynamics, that things go from hot to cold, but they never go from cold to hot unless you add energy. But the natural law of the universe is this law of entropy, which is over time, the natural, the cause and effect. And look, I could go into this and would love to go into this in greater detail because it's a fantastic thing. Hold on, I've got another. Oh, you mentioned entropy. Thanks, Stephen. Entropy measures time's direction. Well, then you're exactly right. The second law of thermodynamics, the law of entropy, says that since the Big Bang, order will always go to disorder. Now, there's a guy called Boltzmann, who is the leading light in entropy. And he says the reason why you can shatter a mirror, but you can't unshatter a mirror, is down to entropy. But it's because there are more possibilities for disorder than there are for order. That is the law of entropy. But this experiment shows, hold on a minute, at a quantum level, time does not exist. That's why we say the universe, people quite rightly, intuitively can't work out how the universe came from nothing. But this is sort of saying that at a quantum level, things can exist before they're there. Subatomic particles can arrive somewhere before they're there. In fact, they frequently do. Paul Dirac, one of my favorite theoretical physicists, who incidentally went to the same school as Cary Grant. Now there's a bit of trivia for you. Paul Dirac, who was a theoretical physicist, he came up with antimatter, he sort of said there's no such thing as empty space because you've got particles coming, quantum particles, quantum foam, coming in and out of existence before they've existed, and it's all weird. Now, I'll just get on, before I take more questions, I'll just get on to the Gedanken. This is wonderful. John Wheeler said, now, we could have a particle coming from a distant quasar 10 billion light years away. And the way we measure it today will affect its fundamental nature on all the journey. I didn't explain that well. It might come 10 billion years as a wave, but the way we look at it now could change those 10 billion years to it was always a particle, not a wave. Because what happens is, oh, I've got a question. Multiverses is probably a different thing, but I know a lot about the multiverse and the many worlds theorem. In fact, one day I'll do a talk on the many worlds theorem. But you're saying that is changing the past. Yes, it certainly appears so, doesn't it? Something strange is happening. We're either rewriting the past or we're predicting the future. And I have to say again, 100% of the time. So thanks for that statement. But what happens is, and this is Einstein's general theory of relativity, when the light bends around different galaxies due to, and we know this is a fact, due to Einstein's general theory of relativity. So the effects of gravity is that will bend light. So when, oh, I better put, let me put my, come on. Let me get my annotation out so you can see what I'm referring to. So, let's say this light will bend around this galaxy because of the gravitational pull of that galaxy. This is why this is why we can see galaxies that are behind, we can see light from galaxies which are in our line of sight of other galaxies because the photons will bend round. So we could have gone this way, or we could have gone that way. Now, we can actually just view it through a radio telescope, and if we do that, we know which way it went. Because we're seeing it, so we're observing it, and we can follow the path. So it went left or right is how it bent around the galaxy. But we have another piece of equipment called an interferometer, which is actually what they use to detect gravitational waves. And Stephen, great question on multiverse. Everybody says we'll never, ever, ever be able to measure whether there is a multiverse, but actually that's not true. We may well soon be able to detect energy from another universe with gravitational waves. Gravitational waves, we have detected gravitational waves at, which is Einstein's famous, incredible prediction. So, you know, when you have two black holes colliding, we can still, even though it's 10 billion years ago and 10 billion years away, we can still measure that vibration. Even though these interferometers can measure to a hair length accuracy from here to the sun, 1 astronomical unit. They're unbelievable, and they are currently, there's one in India, I think. Geez, I might know. Please, I hope I'm not assuming you keep up with Indian cosmology, but there's India are just building a interferometer, LIGO, so it's the laser interferometer gravitational observatory, which a year ago proved the two black holes had collided. Anyway, I also have one more thing. At the moment they're on Earth, but soon we're going to have, it's called LISA, which we will have a laser interferometer space observatory. So in space, we're going to have measure it to even a greater accuracy. Wow. But for the purpose of this, we can measure it with an interferometer. Now, if we do that, we don't know. We can't see the path of the photon. We don't know which way it traveled. Therefore, it's a wave. So this particle may well have been a particle all its life, but we don't know. And if we don't know, it's a wave. So if it was a wave and then we observe it, then it becomes a particle. But for the whole 10 billion years, it was a particle. It's been rewritten. Wow. Oh. So, guys, that's the end of the presentation. Wow. So I hope that has given you some, ideas. I want to unmute you all. Oh, yes. So, look, I've now allowed you to unmute yourselves. So if you have a question, please, you can either put it in the chat or you can unmute yourself and ask it. Oh, Stephen's got one. If we change the past by observing it, I suggest we are splitting our current universe. Stephen, who was that? Someone, I think, just asked to be. Oh no, yeah. Stephen, there's an interpreter. I don't know whether you're aware of this interpretation, which is called the many worlds interpretation by Rupert Everett, which says every time we collapse the wave function, we create another universe. So, yes, you're quite right. Well, I can't say you're quite right, but according to Hugh Everett, I've said Rupert Everett again, haven't I? Because he's the actor. I don't know where I get that from. Hugh Everett, who's the famous, and by the way, he was ridiculed when he came out with this. The beauty of Hugh Everett's many worlds theorem is what he's saying is, I can collapse it, but then I become entangled with the part. I become part of the system, if you like. So, yes, that photon for me is collapsed, but for the rest of the world, it's not collapsed. So somewhere there's a different world where it's not collapsed. And there's a thing called, I don't know, but Stephen, you've heard of it, Wigner's friend, which takes this to one extension. And there's been, in fact, I think my next presentation will be on this. There was an experiment just a year ago that proved objective reality, i.e. that one photon has collapsed for you, but not for me, or vice versa. You can have a remote viewing and a local viewing, and the universe has different realities in it. I hope I'm not getting too much off point here, but yes, it produces many worlds. Now, Einstein would have liked that because you may have heard Einstein, God doesn't play dice quote. And what he meant by that was quantum physics is fundamentally probabilistic. And when you collapse the wave function, we don't know which way it's going to go, but it's 50% chance that it'll be, like when we collapse the qubit, there's 50% chance it'll be 1 and 50% chance it'll be 0. And we don't know. It's probabilistic. Einstein did not like that. He said it cannot be. Now, Hugh Everett's interpretation, and it's only his interpretation, remember, of the many worlds, is deterministic, because he's saying there's no probabilistic, you're just collapsing it for yourself. So it's 100% that you're going to collapse it because you are doing the looking or the not, observing or the measuring, or you're not doing it. But for the other worlds, it remains a state of uncollapsed until they view it or look at it. That's a bit of a convoluted way of saying, yes, Stephen, you're quite right. There could be a universe created every time a subatomic particle is observed or is collapsed. Stephen, intuitively makes sense. I don't think I can agree with you there. I like your thinking, but I wouldn't call it intuitive at all. It makes sense. I'm being a bit rude there. I can see what you mean when you say intuitively it makes sense. But I think you would find most people, when they think about how many universes there should be, by the way, I have an app that literally sends a photon that collapses a universe, a wave function, and I've got it on my phone now, and it will tell you whether it'll create another universe for you. It says in one universe, you're on the right, and the other universe, it's on the left. I mean, we could go on forever. Sheetal, so everything is in superposition, which underlies the many worlds theory. No, not at all. Everything is in superposition until it is measured or observed, or whatever that word is. Now, in the many worlds theory, it's mere interpretation. It's merely saying, for me and my world, that photon is collapsed because I looked at it. But for the rest of the world, it's not collapsed until they measure it and collapse it, or don't collapse it, if you see what I'm saying, Sheetal. So that's why there's many worlds. And then I love the way, I'll just see what Stephen says again. To make sense of this, my intuition tells me this is multiverses. In maths, I was trained to use intuition as a tool, and I took it. Stephen, I'm not knocking it for 1 second. I agree with you totally. And it does make sense, but it's, Stephen, how many different worlds are there? That number, wow, is an amazing number. And it's not infinite. It's not infinite either. Well, no, it's not infinite, Sheetal. Because someone somewhere hasn't collapsed the wave function. So it is a definite number. Sorry, the only thing I don't like about multiverse, okay, first of all, before I go into Stephen, multiverse and many worlds are two different things. Multiverse is a cosmological term that says our universe didn't start from a big bang. It started from a huge inflation. We know this because the universe is in symmetry. It's not like a bang. If it was a bang, it'd be all very disordered. It actually isn't. The universe is quite symmetrical. There's a word for it, which I can't remember now, but anyway, it doesn't matter. It means that it wasn't a bang, it was a huge inflation, and we call it the inflaton. And there's a field, which we're searching for, at the Large Hadron Collider called the inflaton field. It's harder to detect than the Higgs boson. But the inflation has slowed down and expanded, and we're currently, the inflation you can think as repulsive gravity, and it's called dark energy. So dark energy is what is empowering this inflation, and it's captured in the inflaton field. Now, we know roughly where it started and where it's slowed down and where it's accelerated. And at this moment in time, as you may or may well not know, our universe is expanding at a faster pace. Found out by the University of New South Wales, well done Australia, and they got a Nobel Science Prize for that. So there's this field. Now, a multiverse is where we believe that this propulsion, this repulsive gravity, there's no reason to say that it's not happening everywhere at the same time. Ours just happens to be our inflation, and it can exist in a bubble from another inflation. But there's a bit of cosmology for you, which is my background as well. So I've now been ignoring these questions, which is very naughty of me. So let me go back. Yeah, the only thing I don't like about multiverses is how conservation of energy apparently fails. Well, it doesn't. It's the conservation of energy will remain in the individual universes. Then Sheetal says, every possibility of every alternative must justify yes. Immensely. 99.91% of the universe mass is dark energy. Well, no, it's not. It's not as much as that. Dark energy is about 75%. Is dark energy. Dark matter is about 15%. And baryonic matter, which is all the stars, you and I, and everything that's made of mesons and baryons, which are quarks at the end of the day, they account for about 5%. So dark energy 75, dark matter's 20, and baryonic matter is 5. So 95% is dark related. But remember, dark matter, which we're desperately trying to understand what it's made up of. There are a thing called WIMPs, weakly interactive massive particles, and we believe that that's what's causing dark matter. At the moment, we don't know. But dark matter is actually real gravity. So it's not repulsive gravity, it's actually the opposite. It's pulling in the universe. Discovered by a woman, I might add. A man and a woman at the same time at opposite ends of the globe, Chris Wicke, and a woman called Vera Rubin, who only passed away about 2-3 years ago. She was not allowed, she found this out in the 60s. She studied Andromeda spiral, and she said, hold on a minute, these galaxies at the end should be going at different speeds to the ones at the middle. And she said the only explanation is that there's more gravity than we can see. Anyway, let's not go into that. Fantastic. Look, are there any more questions? I'm more than happy to answer those questions. You guys have been great. It's been 1 hour, 20 minutes. And you've all stayed with me. So if there are no more questions, I'll actually conclude the presentation now. I hope you found that incredibly interesting. The main takeaway is that it's unbelievable, yet we can thank you, Sheetal, for your very interesting. The amazing thing is that we can harness these forces to build computers. And that's why our quantum computers, of which there are about 100, 200 in the world at the moment. I might add, Australia is doing great stuff. There's a company called Quantum Brilliance, who I'm talking to at the moment, who are actually doing quantum computers that work at room temperature. They're actually doing them on the impurities or the spaces in between diamonds, the what's called NV, the nitrogen vacancies in the diamond matrices. It's fantastic. Well, that's going to change the world. So, look, it's the fact that we can use these forces to do mind-boggling calculations. Where it's going to go, who knows? Thank you, everybody. Thank you for your attendance. Please give me any feedback. I will send you all a recording of this presentation and the slides, and I look forward to talking to you in the future. Oh, yeah, Stephen, we can talk about that offline. Otherwise, we'll never go. Thank you very much, everybody. Bye now.